So before we talk about what we're going to do today, which is going to include that blue paper that we started on yesterday, we're going to back up a little bit. This is the, this goes with our lesson from yesterday, and it's the part that we'll have on most lessons, which what it might look like on the AP exam. Just some sample questions from past exams. So let's look at number 1. It says the vertical line x equals 5. So, I don't know what's going on up here. Okay. The vertical line x equals 5 is an asymptote for the graph of the function f. Which of the following statements must be false? Okay, those are 2 very important words. Must be false. Okay. So, if I'm looking for if the limit as x approaches 5 of f of x is 0, okay? So, if the limit as x approaches 5 of f of x is 0, what's that going to look like? Could that be true if there's an asymptote there? No. Okay, so if x equals 5 is a vertical asymptote, right, then as x approaches 5, can my limit be 0? No. Okay, so this one I don't like, so it might be my answer, but we always read the rest of them. If the limit as x approaches 5 is negative infinity, that would look like this, then could there be an asymptote there? Yes, so I like that one, which means it can't be my answer. And same thing for this one, as x approaches 5, infinity. So it can't be that one, because we're looking for false. The limit as x approaches infinity is 5. Well, if you have x equals 5 as a vertical asymptote, does that mean that the limit as x approaches infinity equals 5? Could this happen? Are we guaranteed that this would happen? No. So false is an important word here. The other word is must be false. Could this be true? Yes, and it could be false. We don't really have enough information, right? So the only one that must be false is A. Okay, so wording is important there. All right, so let's look at number 2. How many vertical asymptotes does this graph have? All right, well, what would I need to do to try and figure that out? Factor it, okay? So this bottom part here, that is called what? What kind of situation do we have? Difference of squares. So I can get x plus 1 on the top, and then x squared plus 2, no, plus 1, that's dumb. X squared plus 1 times x squared minus 1. Can I factor some more? Yes, I can. So I still have x plus 1 in the numerator. Can I factor this x squared plus 1? No. So that stays x squared plus 1. But then this is another difference of squares, so that's x plus 1 times x minus 1. Does that mean I have 3 vertical asymptotes? No. Okay. Can I reduce this? Yes. When I reduce these here, and this becomes a 1, what does that tell me is happening at my graph when x equals negative 1? There's a hole, okay? Not what this question's asking, but there's a hole there, right? All right, so that means what I'm left with here is that I have 1 over x squared plus 1 times x minus 1. I get my vertical asymptotes from when the denominator is 0, right? So I know I get a vertical asymptote here at x equals 1. There's 1 from there. Does this give me any vertical asymptotes? No. Exactly, so bless you. I get x squared plus 1 equals 0. So that give me x squared equals a negative 1. So x equals plus or minus the square root of a negative 1. That gives me a value, but it's an imaginary value, and I can only use the real values here. So that doesn't count. This is my only 1, and my answer is 1. So you can't go by the degree of the denominator, right? That's kind of what that's pointing out there. Okay. So read number 3. Discuss it amongst yourselves. See what you can come up with here. I love your idea of drawing a graph. Check your domain and check your graph. Right. Listen to the things we know now. X equals lines or vertical lines. High five. Could you have told me that at the beginning of last year? I didn't think so. So good job. See? But you do now. Look how far you've come. Okay. Do we have at least have it narrowed down? Let's talk through this. So they were going to make a graph from the beginning. That's good. Y'all ended up kind of sketching stuff. That's good. That's the way I would do this too, to kind of wrap my mind around it, because if I just plan on what's staying in my head, that doesn't work too well. So I have this function. It's positive, okay? So that means all of your y values are positive. Think about that. And the domain is x is greater than 0. That means all of your x's are positive also, right? All my x's are positive, all my y's are positive. The limit as g of x approaches 0 from the right is infinity, okay? So as I approach, so I know my graph all has to be up here. As I approach 0 from the right, it's infinity. So that means that I have to have an asymptote right here, right? Y'all figured that out pretty quickly, I think. So that means that if I have to have an x equals 0, so that eliminates those two pretty quickly, okay? And if all of my x's and y's are both positive, then that means that I have to have a horizontal asymptote. So I have to have one of these two, right? But then it says the limit of g of x as x approaches infinity. So way out there, my end behavior, it's approaching 5. That means I have to have a horizontal asymptote here at 5. Okay, good job. Listen to that reasoning and that discussion y'all had. That was good. Any questions about that? Okay. You good on that? Said yes. He does have a question? Oh, what's your question? Ask me. Well, okay, what part do we not understand? Because you told me if it's an x equals, it's vertical, right? So this says as x approaches 0 from the right, my limit is infinity. So as I'm getting closer and closer to 0 from the right, my limit is infinity. So that's why that has to be there. Does that make sense? Did you say it one way and think it the other way or something? Okay. Does that make sense now? Okay. All right. We good now? Perfect. Okay. So now I want you to grab your assignment that I gave you yesterday. It's a yellow paper. And we're going to put this one in your ISN. I was thinking about this. I'm sorry. I'm just going to grab this. So what do we put this on? So I was thinking, since you tape that there, if you folded this, you could probably tape that right there too. And then you can just like have all of it there. Does that make sense? Like a little flip book? Because if you just put a piece of tape right there, it kind of tapes it to it. I think that'll work. Okay. We'll just try to figure out what works to kind of keep everything together, and I'm not going to be super picky. You make it work for you, but I want to try and keep us on the same pages so that we can find things easily. Okay, so I know I handed this to you and you didn't really have time to work through this. I don't guess we didn't have any time. I just gave it to you at the end. Okay, so what I wanted to look at was just notation and what's expected of you on how you answer these questions, okay? So we're going to start number 1 together, and then we're going to move on to what we're going to do today, okay? So it says, find the vertical asymptotes and describe the behavior of the graph to the left and the right of each vertical asymptote using limit statements, okay? Using limit statements, left and right. So if I want to find my vertical asymptotes, what am I going to have to do here? Factor. That's very good. So go ahead, and I'll give you a second, and you get this factored and find your asymptotes. And you may need to factor the denominator by grouping. That's totally fine. I'm going to show you a different way. But grouping is fine if that's what you need to do. Okay, so if you factor by grouping, that's great. I heard some discussion. So let's just, a little side note here. Let's talk about factoring by grouping real quick. If I have 2x squared plus 3x minus 5, 2 times a negative 5 gives me a negative 10, right? So I need two numbers that are going to multiply to give me negative 10 and combine to give me a positive 3. And since this is a negative, they're opposite. So I get 2x squared. So that'll be 5 and 3 plus 5x minus, sorry, my brain is minus 2x minus 5. Okay? And then you factor by grouping from there, right? Okay. So there's nothing wrong with that. Okay? But I'm going to show you the old school way that I was taught that I think maybe, especially when this is a prime number, then this way is, I mean, it's kind of a guess and check way, but it's, especially if both of these are prime, it makes this not so bad at all. Okay? So I'm going to ignore the 5 and the 2 in the middle right now because I'm going to pretend like I just started from here. So I know, especially if this is a prime number, like if that was 4x squared, this could be 2 and 2, it could be 4 and 1, like I wouldn't know. But this, one of them is going to have to be 2x and one of them is going to have to be x, right? I also know because of this my signs are opposite, but I can't just plop them down in there. What I do know is that these two numbers have to multiply to give me 5, right? So I can think, okay, it could be 1 and 5. This would be in my head, but I'm just writing it down. So if I did this, this would give me 10 and 1, and those won't subtract to give me 3. So instead I would try 5 and 1. So 2 times 1 is 2, and then 5, and if I subtract it, I'll get my positive 3, which means I want this to be a positive 5 and this to be a negative 1. Okay, and it's just kind of a reasoning process with your numbers. I'm not saying you have to do it that way, but I'm saying if you factor a ton, you kind of get used to how to manipulate the numbers. It gets a little more complicated if this is not a prime number and this isn't either, but that's just something, okay? Not saying you can't do it this way, but make sure you can factor. That's the biggest thing. Okay, so can I reduce anything? No. Which means I don't have any what in my graph? Holes. No holes, okay? That's not what this is asking, but that's something we need to know. So how many vertical asymptotes do I have? 2. So I have my vertical asymptotes at x equals what? 1. And x equals negative 5 over 2. Okay, so I found my 2 vertical asymptotes. Now I need to, it says, describe the behavior of the graph on the left and right of each vertical asymptote using limit statements. So I need to say the limit of f of x as x approaches negative 5 halves from the left equals something. The limit as x approaches negative 5 halves from the right of f of x equals something, right? That's the left and the right of one of them. I don't know why I did the second one first, whatever. And then I also have to do the limit as x approaches 1 from the left of f of x, and the limit as x approaches 1 from the right of f of x. Okay? So I'm showing you this because I don't want you just plopping down numbers, right? You have to have your notation. It's okay. You don't have to rewrite this entire thing. Like, you need all that, but you can just, I mean, it's defined as f of x, so you can just write f of x because that's what we're talking about. You find each one of these, right? So we're going to do that by saying, all right, so negative 5 has us like negative 2.5. If I'm approaching it from the left, I could use like negative 3 even. So negative 3 minus 2, that's going to give me a what kind of number? Negative. And then negative 3 here would make that negative. Negative 3 here would make that negative. When you multiply all those together and divide, you get negative. So it'd be negative infinity. It's kind of like the sign charts we did. Right? Make sense? And then you can go through the rest of those. So I'm not going to do all those for you, but that's what you're going to have to do on each one of them. Do you have a question, Sabali? We all good? Okay, perfect. All right, so put this away for me. And go back and finish this on your own. We can look at it tomorrow. And get out that blue paper we started on yesterday where you filled a bunch of stuff out. I'm not sure that I have the picture of that here. I don't. Oh my gosh, this board. I might scream. Okay, hang on. I got to go back to my desk to do this. All right, so I want you to look at it. I want you to look back over that stuff. Look at those 3 questions at the bottom. Think through it again. Well, I try and... Oh, no, the blue paper you got yesterday. That one, yeah. Yeah, I'm going to give you that. I know you don't have the one I'm showing you up here because I don't have the other one up here, but... Oh, my gosh. Okay, you're going to have to... This is just being stupid now. First of all, somebody tell me what page this is going on. 28? 28. All right, 28. Do your vertical asymptotes affect continuity? Yes. Do your horizontal asymptotes affect continuity? No. Okay, good. All right. So continuity and the types of discontinuity. So continuity is one of the cornerstones of calculus. Almost everything we learn in this class will require us to first consider and often state, legally, the continuity of a function. In some cases, such as exponentials, polynomials, logarithms, and trig functions, we know whether the function is continuous or not. Occasionally, we need to check continuity at a point using the definition of continuity. Okay, so the definition of continuity. A function f is said to be continuous. So this is my definition. Is said to be continuous at x equals c if and only if your first, all 3 of these things have to be true, f of c exists. Okay? What that means is that the point exists. So no holes. The second part to this is that the limit as x approaches c of f of x exists. So the limit from the left and the right have to be the same, and it has to exist. Okay? Then number 3, the limit as x approaches c of f of x has to equal f of c. So what that basically means is that the limit equals the point. Okay. Any questions about that? So f of c has to exist. That's something we can test for. We know how to test for the limits. And then if these 2 things both, we have this exists and this exists, then they also have to be the same. If they're different, that's a problem. Okay? So we're gonna draw these. It says if a function f is not continuous at x equals c. Oh, it was a shoe. Well, she's blessing your shoes. The discontinuity may be one of 3 types. And so the point discontinuity we're actually going to draw two different things here. So I could have something that looks like this, right? I could have something that looks like this. Both of those have point discontinuity, which is also called removable discontinuity, which means basically we just removed a point. And in this case, we removed it all together. In this case, we removed it and put it back right here. So this is C. So let's talk about what this fails here. F of C, here, F of C doesn't even exist, right? So we fail with number 1. Here, does F of C exist? Yes, it's right there. Does the limit of f of x as x approaches c, does that exist? Yes. Are those two things the same? No. And that's why it fails. It fails on number 3. This one fails on number 1. This one fails on number 3. Okay? So this one's usually the easiest one to check. That's why we check it first, and then we just kind of go from there. Okay? All right. Jump discontinuity. Look like this. We could have right, make this C. Does f of c exist? Yes, it does. Does the limit exist? No. Okay, so because it jumps. That's why it's called jump discontinuity. So it fails on number 2. Then your asymptotic infinite discontinuity. Sounds all fancy, doesn't it? So it could look something like this. So on this one here, like, if we worked backward, well, does the limit exist? I mean, yeah, you can talk about it as does not exist. You could talk about it as infinity, either way. But the problem is, if we just start with number 1, if this is, I probably should have moved that over, but if this is C, does f of c exist? No. Okay. We all good with that? Questions? Okay. These should not be brand new to you. We talked about these discontinuities last year. We didn't talk about them with limits like this, but those discontinuities definitely should not be brand new. All right. So a point discontinuity is said to be removable discontinuity because the function can be redefined at the point in such a way as to make the function continuous there. So I could basically just plug this point back in and boom, boom, or just move that one down. I can redefine it and okay, now we're continuous. Jump discontinuities and asymptotic discontinuities are non-removable because the functions which contain them cannot be redefined at a point to make them continuous. Okay? That's why it's called removable. All right. Let's look at this. It says, discuss the continuity of the functions below by identifying and justifying what type of discontinuities exist. Okay, so the first thing we're going to do is see, does f of c, well, I don't really know what c is here, so I didn't write it as a limit. Okay, let's just do this. Does f of 2 exist? It doesn't, does it? Because I have 0. So f of 2 is d and e. Does not exist. So we fail on step 1, right? But it says for us to graph this. So that means I need to factor this. And this is going to be x plus 2 times x minus 2 over x minus 2. X equals. So then these are going to cancel out. So I get f of x equals x plus 2. What is that going to graph? A line. It graphs a line. Yes, but it graphs a line. So it graphs a line. Okay. So, but I have what? What happened when I did this? A hole. I have a hole at x equals 2. So if I go to 2, and then I plug it in, I get 4. See, your answer was right. I hadn't asked the question yet. You're just a genius that way. I can put my hole there. And then, what's my y-intercept? 2. Yeah. Y-intercept. Come on, we're going way basic here. It's a 2, so that's enough. Yeah, it's just, exactly. It's just a line with a hole in it. Okay. All right. So let's look at this one. And if it were, I would rewrite these questions if I had a chance, but I didn't have a chance to rewrite these. Does f of 3, what is that? Yeah, does not exist. Okay, so we're not continuous there, right? What's happening at 3? Not here. Asymptote. What kind of asymptote? Vertical asymptote. You're so funny, too. Okay, vertical asymptote at x equals 3. And there's also a horizontal one at 0 because it is bottom heavy, right? Okay, that doesn't affect my discontinuity, but it does affect my graph. And then this graph is just this. Okay, we good? All right. So look at this one. Does f of 1, what is f of 1 on this one? This one. Is 1 even in my domain? Nope. So guess what? Does not exist. It's a hole. It is a hole. It's a hole right here because it's not in my domain, right? And then x, oh, that's not even at the right place. It would be at 3. Sorry if I did this right. 1, 2, 3. It would be here. And then my slope is just 1. It's basically going to look like this. Okay. All right. Don't tape that in because we're going to do the back tomorrow to get us started because this is the first half of the lesson anyway. We'll do the rest of it tomorrow. Okay? Have a great day. Don't forget your phones. Do something nice for somebody today. Make them smile.